Hi everyone, this is going to be the first seminar of the seminar sessions of the trimester, and we're very happy to have Thierry Levy, who is going to talk about Wilson loop expectations in 2D Young-Mills theory.
Thank you very much, even for the introduction. Thank you all for being here. It's a pleasure and an honor to give this talk. I will talk about Wilson loop expectations in 2D Young-Mills theory, which are quantities that have been presented in several occasions in the last weeks, but I'm not going to rely on these previous presentations. And I want to show you combinatorial formula to compute these Wilson loop expectations. So first I will explain what they are, then I will explain on a simpler example how I intend to proceed to compute these expectations, and then I say enough that I can at least state the formula, and I will not give many elements of the proof. I will try to indicate the flavor of it. So let me start by describing these Wilson loop expectations and this two-dimensional Young-Mills theory. So we are working on a manifold that is a compact surface. And for this talk it will be closed in the sense that it has no boundary. I don't want to have boundary components. And on this compact surface, orientable, maybe it's not essential, we have a measure of area. We are able to measure the area of a nice domain of this surface. We have also a group that I will take to be the unitary group UN in this talk. The story that I'm going to tell depends on the fact that I'm taking this group. There is certainly a similar theory for, a similar statement for orthogonal groups, for symplectic groups. So it could be the special unitary group. I take the unitary group. So n here is an integer. And I need to normalize I need to measure the size of the group in some sense. And I do this by choosing an invariant scalar product on the Lie algebra. This will not appear explicitly later, but still it is a fundamental ingredient of the theory, so I'm describing it. So the Lie algebra of this unitary group is the space, the real vector space of skew Hermitian n by n matrices. And I decide that the scalar product of two such matrices is n times the trace of x star y. So here there is a bit of an arbitrary decision that will have some influence in formulae that I will write later. But again, I will not explicitly rely on this scalar product. Just to give a hint where it will play a role, this determines what I will call the Laplacian of the unitary group later. And it scales the Laplacian. Now with these two things, there is a Young-Mills holonomy process. So for every nice loop on M, it is possible to jointly construct a family of random variables that I denote by HL, one for each nice loop on the surface, and this HL is a UN valued random variable. This is supposed to be an incarnation of the Young-Mills measure, of the pure Euclidean Young-Mills measure in this setting. So there is a well-defined stochastic process indexed by loops with values in the group. If we want to describe the distribution of this process by numbers, then a fairly natural thing to do is to take a finite number of these loops, to take these random matrices and take their traces, that produces a number. We can multiply these numbers, these complex valued random variables, and compute the expectation of this. And this number is one of the fundamental numbers of this theory. It's called the Wilson loop expectation, and I will denote it by WL1LN. I mean, certainly these are natural numbers to compute. You might think or wonder if these numbers are enough to describe the distribution of this family of random variables, and you might find quite natural to not only consider the expectation of product of traces of these matrices, but traces maybe of powers of these matrices. That would certainly seemingly give more information. But in fact, the square of the holonomy along L is the holonomy along L that you've gone twice. This H is multiplicative. If you concatenate two loops, you multiply the random matrices. So in fact, this contains powers of these matrices. Yes?
Sorry, do the loops have a marked point? Or?
Yes, they are based. They are based loops, yes.
You don't.
These HLs shouldn't depend on.
Sorry?
The HLs shouldn't depend on the.
They do up to conjugation, so the trace doesn't.
Okay.
I mean, there are various presentations of the story. You could say that you fix one point once and for all, and you only consider loops that are based at this point.
Mm-hmm.
Conceptually, this is perfect, but practically, this is not very convenient because you always have to, if you're interested in a particular loop, you will have to add a tail that goes to. But yes, so there. And it's these numbers for which I want to write a formula. Now, a formula, okay, but how are they defined? I mean, I'm saying that there is a well-defined mathematical object here, a stochastic process, so certainly there is somewhere a formula for this. So yes, there is. And it's the Driver-Sengupta formula. So this is not a completely official name, but I think it's fair that these two names appear. I mean, Bruce Driver wrote the formula, I think, in the case of the plane, and then Anbar Sengupta adapted it to the case of a surface. So let me give you a first expression of this, and then I will tell you how I intend to transform it and give it a combinatorial form. I will write the formula and comment, explain the elements along the way. So, by definition, so to say, this is equal to, it starts by something that we cannot know what it is, but you know what I mean. I mean, I'm going to write a measure that is not a probability measure, but a finite measure, and we normalize this finite measure. So we have our surface, and we have loops. Okay. We have loops. These are the loops that we're interested in. They are based, they are oriented, but I'm not drawing. Okay. Let's add some. Let's refine. So we are seeing a kind of skeleton of something on the surface. Let me first decide that here we have vertices because something happens at these points, and also let me add a few edges, so that we really have a nice discrete version of our surface, and that we do not have a hole or a handle or something topologically really non-trivial in the middle of a face of this graph. I mean, we want it to be fine enough, so I'm not sure if this one is fine enough. Well, it probably is. We construct a graph on the surface that includes the loops L1 and N. This graph has vertices, it has edges, And it has faces. So the faces are the connected components of whatever is left when I remove the edges. And this number is expressed as an integral over a configuration space which is un, the group, to the power the edges. So at the end there will come a du. And u is an element of this configuration space. So it's a map from the edges to the group. So u is a map from the edges to un. And we agree that if we take an edge backwards, then we have the inverse of the matrix. So this is not written in this notation, but it's we agree on this one. So this is the set over which I am integrating. This is essentially a Cartesian product of finitely many copies of this group un. So there is a uniform measure, that is the Haar measure. So du here is the most natural measure on this space. Now, whenever we have a path C in this graph, and C is the sequence of edges E1 to ER, we have a function on this configuration space, which is a little h of C, which takes a configuration and produces an element of the group, a unitary matrix. We just take the matrices that we read along the edges and multiply them. And for some reason we multiply them from right to the left, but that doesn't matter much. So with this we can write the first terms here in the integral. We will have the product for I between 1 and n. N is the number of loops of the trace of HLI of u. So this is the function that we want to integrate. So this is not yet the measure. This is what we are integrating. And now I'm going to describe the measure. And for this, I need to introduce the heat kernel on the unitary group. If we have a positive time t, I define the function pt as the smooth positive function that I obtain by considering the Dirac mass at the identity matrix and applying the exponential of the Laplacian for a time t over 2. And again, this is a smooth function on un with values in R in positive numbers. So this is the density with respect to the Haar measure of the distribution at time t of the Brownian motion on the unitary group. And the density that we put here, so in fact maybe the du could have, is a product over f, a face of this graph, of the heat kernel evaluated at the holonomy along the boundary of the face in the configuration U, and the time is the area of F. So du should not stand in the middle of the board here. It can actually. So this is the definition.
And it doesn't depend on...
It doesn't depend, thank you, on the way we extended these loops into a graph. That's the reason why this theory works so well, because however you do it, you find the same number. It's invariant under subdivision, which is the dream of every lattice theory, but it doesn't happen often, but here it does.
So you call this two-dimensional Yang-Mills because the measure is coming from the Yang-Mills.
Yes. You can tell a story that relates this to the Yang-Mills functional. So my goal is a combinatorial expression or of z times this Wilson loop functional. So I put the z on the left hand side and I want to have a combinatorial expression of whatever is left on the right hand side.
So, am I correct? I think it's the same question that was just asked, but let me ask it again. So we can think about this WL1 to Ln being defined by this formula, but in fact you could a priori define it using some kind of Yang-Mills measure and then driving some group to prove this formula is true?
They didn't prove in the sense that the other definition is a heuristic. So you can write a functional integral, you can discuss it, and at the end you say, well, this is the sensible definition. So this is really the definition. Did I answer your question, or?
This is automatically consistent.
This, yes. The key to the consistency is that if you split a face in two smaller faces, you replace one heat kernel by two heat kernels, and the two faces have an edge in common, and you are computing a convolution product of two heat kernels, and PT star PS is PT plus S, and the two faces with area T and S merge into a face of area T plus S. So the key to the invariance under subdivision is the convolution property of the heat kernel.
Well, do you still get a kind of good model if you did something where you change this to like an alpha stable process?
Yes, you could replace this by any Levy kernel, provided it has a nice density, absolutely. And the decision to take a heat kernel was Migdal's decision, who analyzed the functional integral and recognized that it had to be convolution semigroup. He looked at it in Fourier terms, and heat kernel seemed the most reasonable thing to do. But absolutely, you can construct a similar theory with other semigroups.
Do I have another question?
No, please.
It's the same question, but in a different way. So if I try and define it via a limit from a lattice version of the 2D Yang-Mills theory with some like suitable nice gauge fixing, can I obtain this expression? Like if I take limits of the Wilson loop observables in the discrete.
Yes, I mean, if you have, for example, specifically the theory that was described by Malin in her course, you do find this as a limit. But there is Malin chose not to have a heat kernel, but another function that tells you whether you are close or not from the identity element. So she replaced the Brownian motion by a random walk. And in the proof, you will prove that this random walk, when you scale it, converges to the Brownian motion. But you could, on the lattice, on Z2, use the heat kernel. The problem is that the heat kernel is a more complicated function than exponential of trace of something. And that's the reason, I think, why many people choose to this I never know if it's Villain or Wilson or whoever action, well, this different action. So you could take any, yes.
Thank you.
Yeah, thank you. Yes?
But in Berlin, course, there was the temperature parameter with
Yes.
we saw this area perimeter low. It doesn't appear here, or is it because then?
It is hidden. You can put, if you have a temperature, it will appear here as a multiplicative factor in front of the area. And so this means There is a temperature which is the total area of the surface, so to say. So, for example, okay. So if in the functional integral you put a beta or a t at the point where you normally would in the exponential minus 1 beta action, it will end up here in the translation process from heuristic to rigorous. So yes, there is a temperature. Now, to come back to the second part of your question, area or perimeter law, this theory in 2 dimensions is very specific in that it is very it is not rigid. It is very soft. I don't know. It doesn't mean anything. The only structure that you need on the surface is a measure of area, and the distribution of the process is invariant under area-preserving transformations of the surface. In particular, you do not need to know how to measure a length to construct this process. So essentially, length doesn't mean anything. So this is a situation where we are always in area law regime, because there is only area. In Yang-Mills in 3 dimensions, you need more structure on M. You need a Riemannian metric. You need to be able to measure areas, lengths, angles, whatever. And in 4 dimensions, also you need a Riemannian structure, but you do not depend on the whole structure. It's a conformal theory, so it's yet another story. But 2-dimensional is very simple. It's almost a topological theory. So you do not expect a perimeter law because there is no perimeter. Actually, I always wonder, and I know I asked this question once in an audience where Antti and Christophe Gardon were there, and I think they answered this question, but unfortunately I didn't understand the answer. I don't really understand how one expects a transition from area to perimeter law in 4 dimensions for a theory that is conformally invariant. And so conformal means that lengths, areas are defined only up to something. So I'm sure I'm missing something, but the point I am emphasizing here is that each theory depends on a certain amount of structure on the space where you build it, and you cannot expect at the end that it depends on more, that whatever you construct depends on more than what you're given at the beginning. And here we are given very little. We have the topological structure on the surface and a measure of area. Okay.
Maybe a basic question. So why do you have a capital N for the inner product?
Because it's convenient in the large n limit. And so this is the normalization that makes it easy in the large n limit, when n tends to infinity. It's the right normalization of the size of the unitary group that makes Brownian motion on this group explore in a macroscopic time that is neither infinitesimal nor extremely long, a positive proportion of the unitary group. So when n is very large, that's you expect you need the diameter of the group to be scaled like this. This is the regime where the Brownian motion on the unitary group will have a limit in the non-commutative probabilistic sense to a free unitary Brownian motion.
But here it did not appear.
No, it did not appear. It will appear if I ever... No, but I like to have more questions if you want. So yes, it did not appear, absolutely. It competes with the area because it also scales the speed of the Brownian motion, and so does the area of the surface. So it's a balance between the two. Okay, so
So it does appear in the Laplacians. That's really what you're saying.
Exactly. This n determines, if we change this normalization, we scale this, we change the Laplacian and we change the speed of the Brown immersion. So, yes. So it's so any change in this factor can be compensated in a change of the area. But if the area is fixed and n tends to infinity, this is very hard to do. I am not going to let n tend to infinity in this talk, but so it's just very often one likes to work with normalized traces, which are 1 over n trace of something, which is a very sensible choice for an immense quantity of problems. But here, this is the right normalization.
You always multiply by n squared.
Absolutely, this is a possibility.
Well, that's what we do.
Okay, so let me describe a toy model of this problem, which is maybe also interesting in its own right as a one-dimensional analog of this two-dimensional Young's theory. It's the stationary. I'm sorry, I don't know how many ends stationary has. Well, Brownian bridge. On U1. So I'm taking this problem and I'm simplifying it in two ways. I take capital N equals 1 and I replace the surface M by a circle. So what I get is a stochastic process xt that is now indexed by a time, and this time has a period 1. So it's itself indexed by a circle, and it's a U1 valued Brownian bridge. So it's really, and it's stationary in the sense that for each t, the distribution of xt is uniform on the circle. So it's well, it's pretty much what you imagine. You have something, I don't know. Okay. Let me write a concrete expression for this. And I hope that the analogy with the Young's case will be clear. So I take any test function, I take times t1, tn, and the expectation of this is 1 over z, a certain normalization constant, and I didn't say it in the Young's case, but it can be computed explicitly, so in here it's even simpler. And we have a u1 to the power n of f of x1 xn. This is the function that we are integrating, and now we have a product. Well, as you expect, a product for k between 1 and n of the heat kernel on u1 at time tk plus 1 minus tk of x k minus 1 xk plus 1 dx. It's really the same thing. Now we have a circle, and for each point on this circle we have a random variable. And to express this expectation, I look at the circle and at the points that we have put on the circle, and the complement on the circle of these points are just a union of segments, which play the role of the faces in the two-dimensional case. And we are taking heat kernels at a time that is the length of each segment, replacing the area of each face, on the increment of x along this segment, and the increment, well, the product of the u's around the boundary of a face is a kind of two-dimensional increment of the polynomial process. So this makes sense. It's
What are the loops, I'm sorry, in this example?
so sorry.
What are the loops in this example?
The points, the times t.
I thought a loop is a map from 0, 1 to the group. So the group here is a circle, I understand, but how the loops are the t's?
Actually,
the loops are degenerate, no?
No. Let me very okay. Let me adapt my analogy. A loop is a map from the unit sphere of R2 to a surface. The circle is a unit sphere of R2.
Okay.
Now let's take the unit sphere of R. That's 2 points, 1 point plus and 1 point minus. So a loop in one dimension should be 2 points. One beginning and one end.
I thought the loop was supposed to map into U1 in this case.
So in dimension 3, the loop
It
would
start and end at the same location. I thought that was a loop. So I don't see, I still don't see.
I see.
The difficulty translating.
I see. Okay, let's not stay lost in translation, but
Okay, if it's not important.
no, yes, I think.
But then maybe if you take a loop, you define your observable now as you integrate the logarithm of the thing along that loop.
Maybe something like that.
Something
I could
like that.
understand, but not in this interpretation. I cannot see how the loop corresponds to a time, to a particular time.
But maybe you still have loops, but the point is that the time is enough.
No, I don't understand your comment with the logarithm, but you do. So the analogy is this. I'll use colors to.
But in
Now
dimension
this is not U1, maybe this is important. This is not U1, this is R over Z. Here a source of confusion is that the index set is the same as the set of values. This is time. This is not angle or whatever we call it.
Okay.
So this is the time parameter of a Brownian bridge that moves in a circle. So I'm doing this gesture because I have a picture of a torus, which is this circle times this circle, and I'm drawing the graph of this. I mean, if you... And HL1 is UN valued, and XT1 is U1 valued.
And so in this case, the D is 2 points.
That was Offer's suggestion. For the moment, it's 1 point, but I'll come back to the 2 points. Oh, you know what I mean? It resulted from this.
I have a more basic question. So this should hold this formula if f should somehow be invariant under rotating all the points x1 to xn.
Not necessarily, but the distribution of the process is invariant. I agree. I mean, so I think unless I'm mistaken, I'm taking this as the definition of the finite dimensional marginals of this process. And I observe that if I multiply
Sorry, I didn't realise you were taking that as the definition. I was thinking there was some
mysterious functional integral, maybe.
Yeah. Well, there's a, just a.
And this is a definition. It's This is a Brownian bridge. I want time and space to be periodic. So it has to come back to its initial point, but mod 2 pi. So if we unwrap it, it's a Brownian bridge on the interval 0, 1 that is conditioned to reach a multiple of 2 pi.
Yeah.
And then I say, oh, if I have this, I can take e to the I, this process, it takes values in u1, and in fact I take it as a periodic function. And I'm saying that if we do this, the distribution of this process will be this.
So if M is a 3D surface, loops are now 2D loops?
Maybe. Yes, I mean, that's absolutely the logical...
But N has completely disappeared from your formula.
Which
Capital N.
Yeah,
It's
'cause it's one.
completely
It's equal to 1. It's equal to 1 now.
No. Here you have, yeah, so I'm still. No.
I guess what I was trying to say, so if you think about the stationary Brownian bridge as being defined the way you defined it, so you start it, say, at 0 and condition it to be somehow you fixed, that like the point 1 is
Absolutely.
equal,
You're right.
so it should somehow be viewed up to a global shift of...
Absolutely. What I said was wrong. I should take actually a uniform in 0 to pi,
Right, okay.
and I conditioned it to reach something plus a multiple of 2 pi. Absolutely. In this sense, that is stationary. Every xt is uniform.
Yeah.
Yes. Is it hot in here, or is it just me?
Yes.
I think it's hot and it's hotter for you.
We can open the window.
We can also try and turn the air conditioner.
Oh, but that makes a terrible noise. If we can open the window, if it's not too much of a problem for the people sitting at the back, maybe it helps.
They can
Okay.
Well,
It worked, it's fine. Thank you so much.
Okay, now what are we going to compute about this stationary Brownian bridge? We might think that a natural thing to compute is the expectation. So it's u1 valued, so I'm happy to think of these of u1 as a subset of the set of complex numbers. So these are a complex valued random variable, so I can multiply them. Well, it's a group anyway, but I mean I can take the expectation. We might think that we want to compute something like this, and that would be analogous to what I wrote in the Youngman's case. Now this is 0 because of the invariance under a rotation shift of the process, because this is equal to e to the I n theta itself for any theta. So this is 0. If we want to have something non-zero, we need to put exponents and to make sure that these exponents add to 0. This is the only case where we will find something possibly non-zero. So we need to but this is relating to this two-point story, because having exponents with sum 0 means that you can describe them as a sum of 1 here and minus 1 there, and 1 here and minus 1 there, and so on. So you could think that we are taking xt2, xt1 minus 1, xt5, xt3 minus 1, and so on, and this will allow us to build any combination of this sort. And in this sense, I think that this zero-dimensional sphere point of view as being 2 points with a sign is a good one. Okay, so let's compute this. To compute this, we need to deal with this heat kernel here, and I'm going to write a formula for this heat kernel. Here I'm working on the circle, so I'm describing the heat kernel on the circle at time t. Pt of ei theta. So if I think of it as a distribution of the Brownian motion, and I think naturally that the Brownian motion on the circle is just exponential I, the Brownian motion on the real line, then I will say that this is the sum, or maybe 1 over root 2 pi t, well not maybe, exactly, sum over k in z, which is, okay, e to the minus theta plus 2 k pi squared over 2t. Now this is a true expression, this is periodic, and this is, okay, this is, I am thinking of the heat kernel as coming from the heat kernel on R by wrapping it around the circle. Now this is not the expression that we're going to use. We are going to use a Fourier expression of the heat kernel that we can find from this expression by Poisson summation formula. I will explain again later how it arises, but we find a sum over r in z, which is a different parameter, of e to the minus t r squared over 2 e to the I r theta. This is also a natural expression, as I'll explain in a minute. But in any case, you can go from this to there by Poisson summation. The thing that tells you that the sum of f of n equals the sum of f hat of n up to some constant. Good. I am going to use this expression in this integral. This means that so we have one heat kernel for each interval, and we are going to expand each of these heat kernels in Fourier mode. This R is a Fourier mode, so we need to choose one Fourier mode for each interval. So here we find 1 over z. Maybe I should put the z in front of it, since we don't want to worry too much about it. So we start by choosing n Fourier modes, one for each interval, because there are n points, hence n intervals on the circle. We collect whatever is a constant in front. These two exponentials do not have the same status. This is a coefficient and this is a function this is the Fourier mode and this is the Fourier coefficient. So I collect the Fourier coefficients, and this produces e to the minus 1/2 sum over the intervals labeled by k from 1 to n of t. T is the length of the interval, that is tk plus 1 minus tk. R is the Fourier mode, rk squared over 2. Good. And then we are left with the integral we have one variable for each time. We have x1, x2, x3, etc. And there are many terms, but I am going to write them not all. I'm going to interlace them so that we see more clearly what happens. Let me focus on the term xk. Xk corresponds to the time tk. It comes with the exponent ak. Then we have the heat kernel on the interval between tk and tk plus 1 that will produce a xk minus 1, xk plus 1. And
The RK, something else?
sorry?
To the RK or?
Okay.
To the RK, thank you. And in fact, I'm sorry, I didn't write them in the right order. Okay, it's okay, it's commutative, so we can handle this. There is also the increment coming from the previous interval, which is xk minus 1 xk to the rk minus 1. And this term should have been before, because I'm taking interval point, etc. dx. Sorry, this does not look as nice as it should. Yes. Okay.
Well, here everything is commutative. So
Everything is commutative, so it's perfect. We don't. This is correct, but not ideal from the optical point of view. But so dx means dx1, dx2, dxn. So we integrate with respect to each variable, and I want to focus on what happens when we integrate with respect to xk. xk is here, and it appears exactly 3 times. It appears once because we have xk to the power ak, once because we have the increment over this interval, and once because we have the increment over this interval. And none of the other terms involve this variable. So we have all of them here. So we can perform the integration with respect to xk, and this is very simple because over u1 the integral of z to the n is 0 or 1, so it won't be too difficult. We just need to check the exponent, and we see that this is not 0 only if rk equals rk minus 1 plus ak. Rk equals rk minus 1 plus ak. Because up to a sign, the coefficient, the power, the exponent of xk is the difference of these two terms. So the Fourier modes cannot be chosen arbitrarily. They are constrained by the powers that we chose in the computation. And in fact, once we've chosen one of the Fourier modes, all the others are prescribed. And since things must come back to their initial point, we need to have the sum of the AKs to be 0, otherwise there would not be, I mean, we find again that if the AKs are not, do not add up to 0, there is the integral is 0. So altogether, this integral is equal to 1 if this condition is satisfied, 0 otherwise. So we find it's the sum that looks like it's a sum over n parameters, but in fact it's a sum over only 1 because we insist that rk is rk minus 1 plus ak times exactly this, which I'm not writing again, times 1. And 1 is this integral when it's not 0. Okay, it's not a fascinating formula. It is a formula, and the reason I'm describing it is that it is this kind of computation that I want to perform in the UN case. So what are the features that we have here and that we will have in the Yang-Mills case? So the first feature is that we have a sum of one Fourier mode for each interval. And as you guess, we will have one Fourier mode for each phase in the Yang-Mills case. Each Fourier mode brings an exponential quadratic contribution. This is the e to the minus 1/2 something. This is this. I say quadratic because it's yes, it's kind of square. Okay, quadratic contribution. There is a compatibility condition between the Fourier mode, which is written here. Given the particular exponents that we've chosen, the Fourier modes need to satisfy this for the integral to have a chance not to be zero. And in fact, when the compatibility condition is satisfied, the integral is equal to 1. Now, in the Younger's case, we will have one Fourier mode for each phase, as I said. It will still be the case that each Fourier mode produces an exponential quadratic contribution. There will be a compatibility condition which will be analogous but more interesting. And when this condition is satisfied, the integral will not be equal to 1, but will have a more interesting value. I know that this is not the mini course or whatever, but I mean, I'm very happy with the pace of the talk. It's not for me to say if I'm happy or not.
We are happy.
But I could almost not, but rush like mad to write a formula, or just go as it goes, and maybe we continue tomorrow. Does that make sense? Okay. Okay, so I'm not trying to finish. I'm trying to make things as clear as I can, and we continue. I finish this tomorrow.
So if you took a different diffusion than motion,
Yes.
maybe you will not succeed in writing a formula like that? Or?
No, because it's. You will have a Fourier expansion. The thing is that the Fourier coefficients will be different, and these Fourier coefficients are very nice combinatorial numbers, quantities, and so on. And there are some very special relations between Brownian motion on the unitary group and Brownian walks on the symmetric group that might not be available if you use a different transition kernel. Okay. So I want to write a dictionary. It wasn't maybe very obvious in the computation that we just did, but we used, in fact, quite a lot of facts about the harmonic analysis on the circle. And we need the corresponding facts on UN. So I want to list a few facts about harmonic analysis on UN in analogy with the U1 case. So of course it will be very sketchy, but it's the Fourier modes on U1 are given by one integer. This is the R that we had before. This means that for every R, there is a nice function on U1, which is the character, etc. I will write it in a second, but Fourier modes on UN are parametrized in many ways, but one convenient way is to parameterize it by sequences, non-increasing sequences of integers. So of course, when n equals 1, the two columns should coincide, and so far it's the case. there is this function that I call m for mode, for want of a better notation. If we evaluate the rth mode on e to the I theta, we find e to the I r theta. This is the rth Fourier mode. Well, it's the same on un. For each mode, there is a function, it's called the Schur function, associated with this particular mode. And when you evaluate it on a unitary matrix U, it produces a complex number. And this complex number, I'm writing the formula not because I'm going to use it, but just to show that it's a concrete, it's not simple, but it's a concrete thing. It's the quotient of two determinants. It's the determinant of zi to the lambda j plus n minus j divided by the determinant of zi to the n minus j. And z1, zn are the eigenvalues of U, so these are complex numbers of modulus 1. So you take the matrix U, you compute the eigenvalues, and you evaluate these two determinants, and the quotient is this function. And actually, it's a polynomial function in Zi. It's a very beautiful, it's a part of the very beautiful theory of symmetric functions. So this is the Fourier mode on UN. We used the fact, I didn't say it explicitly, but we used the fact that the Fourier modes are eigenfunctions of the Laplacian. And the R squared that appeared in the heat kernel expansion is the eigenvalue corresponding to this Fourier mode for the Laplacian. The same happens here. These Schur functions are eigenvalues of the Laplacian, and here I see the same n, the n from the beginning appears here, so there is a number that I call q lambda, q like quadratic. 1 over n is because I chose this n at the beginning, and I'm writing q lambda, again not because I'm going to use it, but to show that it's not a terrible function. It's the sum over I of the lambda I squared plus the sum over I smaller than j of lambda I minus lambda j. So this is an explicit expression that replaces this r squared. And again, it should specify to this left column when we take n equals 1. There is another, maybe more hidden fact, is that when we evaluate the Fourier mode at 1 on the circle, we find 1. And this is because every irreducible representation of this group has degree 1 because it's an abelian group. UN is not an abelian group, and these functions, which are the characters of the irreducible representations, they give you the dimension of the representation when we evaluate them at the identity. And this dimension is not 1 anymore, it's a number, d lambda. And d lambda, I'm writing it again, it's the product for I less than j of lambda I minus lambda j plus I minus plus j minus I over j minus I. All these formulae are essentially due to Hermann Weil at the end of the 19th century, and they are very classical. Why are these functions good functions? Well, one reason why they are good functions is that they are orthogonal. If we use this, if we integrate, here I'm in the U1 column. If we integrate over U1 R the product of two characters like this is 0 unless they are the same. So they are really orthogonal functions in L2 of the group with the Haar measure, and the same holds on the unitary group. Now let me derive the expression of the heat kernel that we used on the right using these facts. So this is the Kronecker symbol, and this is the Dirac mass at 1. Okay. Let me consider this function on U1, this distribution on U1. Let me write the Fourier series of this distribution. This tilde means Fourier series of. How do you do this? Well, you evaluate each Fourier mode on this distribution, and this gives you the coefficient. When you evaluate this on the mode MR, you find MR of 1, which is equal to 1. So every coefficient is 1, and you find this. And now apply the heat semigroup. We know all these functions are eigenfunctions of the heat kernel, so we see that Pt of Ei theta. Now it's an equality because the Fourier series is indeed convergent. We have the 1 gets multiplied by E minus 2r squared over 2 EIR theta. So using the information in the left column, I can recover this expression. Let's do the same on UN. Let's write the Fourier series of the Dirac mass at the identity. Again, it's a sum over all Fourier modes. I didn't give a name to the set of Fourier modes, but it's a sum over the set of Fourier modes of the mode times a coefficient which is the result of the evaluation, well, the pairing of this function, the mode with this distribution. This is S lambda of 1, so this is the dimension. So now we do this 1 that we did not see in the U1 case is now a dimension. So there is an integer in front of each Shor function. And now we can apply in the same way the heat kernel, the heat flow, the heat semigroup to this function. And we find e to the minus t over 2 q lambda d lambda s lambda of u. This is exactly the analog of this. R squared is now replaced by this bit more complicated function. A 1 that we didn't see is now an integer that's a bit more complicated than 1, but okay. And we have the Shor function. So far the analogy is very close, and things on the right are more complicated than things on the left, only because formulae are a bit more complicated, but essentially the situation is not much worse. The point maybe where things are really not as simple on the UN side is when you start to multiply modes. Because on the U1 side, if you multiply MR by MS, you find MR plus S. And this we used because we integrated here a product of 3 modes. And to integrate the product of 3 modes, you need to multiply 2 of them and compare the product with the third using the orthogonality, so to say. So you can write this integral of MR, MS, M. Okay, t is now an integer, I'm sorry. And this is r plus s plus t 0. This is really what we used in the one case. Now the rule for multiplying Shor functions is more complicated. It has coefficients that are not simple coefficients. And these are called the Littlewood-Richardson coefficients. These are, let's say, complicated combinatorial numbers. And because of the toy example, we know that when we try to deal with the Yang-Mills case, we are going to multiply 3 Shor modes and want to integrate them. Fortunately, one of them will be simple, and we are going only to need one of the very simple case of this formula, which in general, again, is complicated, but it has many simple cases. But I suppose this is a...
The point is that these 3 are always adjacent, even in the UN case.
Yes, because in the UN case, you have one integration variable for each edge.
Yes, and the
2 faces. So you have the loop, the face on the left, the face on the right. So it's also 3. It's not 4 or
No, it's
whatever.
also 3, but not only it's 3, they are adjacent.
They are-
It's older, because things are not commutative.
Yes, things are commutative. You are multiplying numbers at this stage. So you multiply functions. So
Okay.
you have S lambda trace S mu of something.
Okay, yeah, thank you.
I think it's a good point to stop.